So today we're looking at the perimeter and area of polygons, just kidding, it's perimeter. So as we look at this thing, we are basically saying what is the outside, and that's all the side lengths added up. So when we talk about perimeter, we're just talking about take all the side lengths and add them up. On this scalene triangle, for example, we have A here, and then we would have B here, and last but we have C as well. So if I wanted the perimeter for this thing, it's just A plus B plus C. Now this varies a little bit if I do know something about the triangle, such as for an isosceles triangle. So for my isosceles triangle, I know it's going to have two congruent sides. Those are the two legs. So that's going to be whatever length it is, and I can represent that by just using 2 times the variable. If you still just wanted to call this S plus B, that's fine. It's just that we'll then combine the two S's together. And if you wanted to call it like A, B, that's fine as well. Doesn't matter what variable you represent it with. Equilateral triangle is helpful because we know in this it's going to have all 3 sides the same. So instead of talking about perimeter as S plus S plus S, we can just say it's 3S. Looking at quadrilaterals, it's pretty straightforward, same sort of deal here. So I'm taking A plus B plus C plus D. This is for a general quadrilateral. I don't know anything about it. For rectangles, I know a little bit extra about this thing, and I know a little bit extra about parallelogram, and I'm talking about these two kind of in tandem here because I talk about their perimeters the same. So I know these two sides opposite are going to be the same because this is a parallelogram. I know the same thing over here just for a general parallelogram. It's just that my rectangle has right angles. So when I look at this thing, it's going to be 2h plus 2b. Over here we're calling it 2b and 2s, but again, it's just because the opposite sides are the same. So if I gave you this side and this side here, you'd be able to tell me the whole thing. Versus if I just gave you 2 of these on a quadrilateral, you would not be able to, because in a just general quadrilateral, we don't know a relationship to these 2 missing sides. Now for a square or a rhombus, we have all of our side lengths are the same. So when I want to talk about the perimeter of this thing, I'm going to be talking about just one side times 4. So if I told you, oh, I have a square with a side length of 10, you immediately know it's going to be 4 times 10. So the perimeter of that square would be 40. Looking at an example here, we have a triangle. So here we're going to call AB 5, and we're going to call AC 6. And we got BC at 7. So I'm just underlining this full length BC so you're not confusing it with BD or DC. And now how do we figure out what the perimeter of this thing is going to be? We just add them all up. So 5 plus 6 plus 7 gives us 18. And we see that right here. So in the next problem, it's a little bit more interesting here because we have an altitude where AD is 8 here. So now I'm going to be looking at this as 8, and then I've got BC, which I'm told is 6. So along the bottom here is 6, and I'm also told that AB and AC are the same. So I'm going to put a little 1 tick here and a 1 tick here. So as I look at this thing, I know this is a right angle. So as I'm given an altitude, I'm given a right angle intersection here, it's perpendicular. This creates a smaller triangle for me, which we'll draw out here, which is that I've got AD as 8. I have a right angle, and then I know that my base angle, or my base side here is being bisected. So here now is 3, and I can take this and just do my quadratic form, my Pythagorean theorem to get my missing length here. So AC will represent just with X. So as I set this thing up, I'm going to basically be having 3 squared plus 8 squared equals X squared, and we see all of that done out here. So I'm going to kind of assume we know how to do this at this point, but if you do want to reference the steps, they're right here for you. So once we know those lengths, we're just going to add them up. So once we get the AC is root 73, I have root 73 here, I got root 73 here. So I have 2 root 73 plus 6, and that would be my final answer. So this is what I'd be looking for on a test. No approximation stuff. But who knows? Maybe it varies depending on what you're doing. Here we have the perimeter of something that's a little bit more complex. So this one's interesting because I've got a length here of 18, a length here of 20, a length here of 12, I don't know what this height is, I don't know what this distance is, and I do know that this is 12. So when we're setting up a problem like this, we kind of want to break this down into mini rectangles. So as I look at all these angles, these are all right angles, no like trickery here. So when we're setting this up, basically we're just going to try and use this floor plan to figure out how much, with the amount of baseboards are needed to do the room, and we don't want to make any allowances for doors. So we're just basically saying like fill the area, box the person in sort of deal. So then we'll just figure out the cost based on the price per linear foot. So when we're doing this, baseboard just is going around the room, just so people know what a baseboard is. It's kind of the thing, if you look at your wall, it's the like pretty white trim at the bottom or whatever. So when we're doing this problem, I just am basically looking for the perimeter. So if I want the perimeter for this thing, I'm going to draw out one rectangle, which is going to be in red here. And I know that my rectangle is always going to be same sides congruent. So if it was 12 up here, it's 12 down here as well. For 18 over here, it's 18 over here as well. Now that gives me some piece of information in regards to what's left over after this 20. If this whole distance here was 20, and then this chunk of it is 12, that means this little piece here is going to be 8. Actually, I should use another color. So that means this distance right here is going to be 8. So that 8 comes from the fact that I know the fold is 20 and this part's 12. So if this is 8, that means this is 8 as well. And if I know this is 12 here, then this will be 12 here as well. So just to note, this 12 different than this 12 over here. This 12 was given to me from this length, this 12 given to me from this length here. So just FYI. So now we can start filling in some missing lengths on the left side here. So if I know that this height here is 18 and this height here is 12, to fill in the missing gap here, which I'm going to represent in blue, I'm going to do the difference of those two things. So again, up to the top here would have been 18, up to here is 12, so that means this is going to be 6. And I already know that this length here is 8. So filling in this chunk here, I'm able to say this is 6 as well. So this is 8 here, this is 6 up here, this is 12. And now I can talk about the perimeter of this thing. So to do perimeter, I want to be coming all the 20. So I'm going to be having 20, and I'm going to say plus 12, plus 8, plus 6, plus 12, and then plus 18 here. So we add all that up right here, and we get 76 linear feet. So 76 as a perimeter for this room, and if I want the cost, I'm just going to multiply that by my 1.32, and it gives me $100.32. All right, so here's where I'm going to balance my inner math nerd with the practical applications for this thing. We're going to use Heron's formula. It's a super useful formula for talking about the area of a triangle just based off the side lengths, but I'm not going to go through and prove the entire thing. It's just a bunch of algebra. I do feel, again, a math nerd obligation to show you at least the reason behind it. So I'm going to show you that below. But basically, I want to talk about what this thing is and how easy it is to use. So if I have just a general triangle here, I mean, it looks like an equilateral, but we're just saying this thing is like a scalene triangle. So I have side length here, which I'll call A. I'll have a side length here, which we'll say is B. And then I'm going to have a side length here, which is C. So as I'm looking, I don't really love where that C is. Let's do it up here. So I have A, B, C for these side lengths. Now, when I'm looking at a triangle, I know how to find the perimeter. So the perimeter of this thing is just going to be, perimeter is A plus B plus C. And now I'm going to introduce a new concept, and that's a semi-perimeter. A semi-perimeter equals 1/2 of the perimeter, and so that semi-perimeter equals 1/2 of A plus B plus C. So this S in my formula is the semi-perimeter, and that's where that comes from. So when we're doing this, the area for this triangle, so when we talk about area, we use this uppercase A here. The area is equal to the square root of, and now this is all being multiplied. So I got the semi-perimeter by itself times, and now again, this is in parentheses, the semi-perimeter minus A times the semi-perimeter minus B times the semi-perimeter minus C. Keep in mind, this is all underneath the square root. So when I go to do this, I'm basically going to start my problem by adding these things up. That gives me my perimeter. Then I'll divide it by 2. That gives me my semi-perimeter. Now I'm going to use semi-perimeter in all these places where I see my S value. I'm basically just going to math my way through this thing and then simplify, and that's it. So a really easy way of finding the area of a triangle. Now I am going to show you the algebra, and there's other ways of doing it too. You could do it with trig, but I'm just going to show you the algebra way because this is the one, if you were to kind of like understand it at this point in your math career, this would probably be the most likely to make sense for you. So again, if you want to check this out, pause the video, take a peek, but I'm going to kind of zoom past it. Just more concerned that we're able to use it at this point. So here we're going to take a peek at actually applying this thing. So here I'm going to represent all these values. So I'm going to say this is my A value in red. I'm going to say the 13 is my B value. And I'm going to say the 15 is my C value. So I'm going to plug in all these different values. Actually, I should have kept these the same. A, B, oh, I lucked out. Perfect. Cool. So all my colors are going to line up because I didn't want to write this thing out. It'll just take me forever to write it out. So the first thing I'm going to do is I'm going to add all these up, and then I'm going to divide by 2. So that's to give me my semi-perimeter. So here's the 4. Here we got my 13. Actually, I should go through and underline all of the values that I want as I'm going color to color here. I want that 4. And we'll grab our 15 here. So adding those things up to give me my semi-perimeter. So the semi-perimeter for this thing is going to be this 16. So as I look at my semi-perimeter, every time I see an S in this equation, I'm going to plug in 16. And let's finish up our color scheme with A, B, and C here. So hopefully this isn't too hard to follow in terms of what these are doing. It's all just each chunk being multiplied. So I have 16 times whatever 16 minus 4 is, which is 12, times, and then 16 minus 13, which gives me my 3, times 16 minus 15, which is 1. So now I have the square root of 576, which here comes out to be a nice 24. And again, that's units squared because we're talking about the area of this triangle. Here we have a version of this which works for all of our cyclic quadrilaterals. So this part here is important. It doesn't work with just all quadrilaterals. It has to be a cyclic quadrilateral. So in my cyclic quadrilateral, I have sides A, B, C, and D. So as we look at this thing, it is virtually the same as Heron's formula, except that one S that was sitting out lonely in front before is now going to be S minus D, my fourth side. So as we look at this one here, it's going to basically be the same, just that I've now got a fourth side for it. So again, very similar formula, very similar process. S here is still representing semi-perimeter. So S is still just going to be 1/2 of the perimeter, which would be all of those things added up. And again, that's getting used here, 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 and here. So super similar to triangle. I'm not going to do an example for this just because it would be pointless for me to kind of run through and just plug in the numbers for you. It's basically just taking cyclic quadrilaterals, again, got to be a cyclic quadrilateral, and applying this formula here. And I'll give you the area of that quadrilateral. Here we're going to talk about the area of a trapezoid. I like to look at the picture of this before I kind of try and lose myself in what each of these pieces are, but hopefully it's fairly straightforward and we've kind of probably seen this before. So when we're looking at this, just some subscript symbols here. D2 they're calling the second diagonal, B1 is what they're calling the first base, and A is just the area of the first triangle. So in this proof here that we're going to look at, this is just the notation they're using. But it's all stuff we've kind of seen before, and it should be fairly self-evident because we'll have a line like this and they'll refer to it as a diagonal. So here we got the area of a trapezoid which has bases B1 and B2. It doesn't matter which one is B1 and which one is B2, but what does matter is we're using altitude as our height here. Okay, so this is H and this is the altitude of this thing. So in this example here, figure 8.21, the altitude would be AE. So again, it's the thing that defines how tall this trapezoid is. It is not either of these legs. It is not BC and it is not AD. So the area of this trapezoid is 1/2 the height times the sum of the bases. So basically I'm going to take AB plus DC, divide it by 2, and multiply it by the height. That's the area for my trapezoid. And here is the proof for that. So we've done a very, very similar set of things to this, so I'm not going to spend a ton of time here, but I do want to kind of go through it with you. So first we're just given this trapezoid. That means that AB and DC are going to be parallel. I have AB, which is just given to me as B1. Again, this is just to note this is our base. And I've got DC, which is going to be B2. So this is my second base down here. B1, B2, again, interchangeable, doesn't really matter. But H here matters, and that's the altitude. So the first thing we're going to do is we're going to draw in our altitude. So that's this height H here. Now, as we look at this thing, for what we know so far, we can say the area of ADC is going to be 1/2 base times height. So here's just talking about triangle things. So ADC here is just a triangle. So we know that that's going to be 1/2 the height times B2. And we can also do the same thing for this triangle on top here, which I'm going to outline in green. So ABC, again, is going to be 1/2 base times height. The height for this triangle, again, is just A down to DC here. It's H. So both of these are using either, one other way to draw it out would kind of be to represent it like this. So if I had this line segment continued out, that this is the height. Again, height same over here as it would be over here if we were to extend out this line segment. So if I've got this ADC value and I have this ABC value and I were to add those two things up, this is what we would be doing. So here I have this area plus this area here, and I've got this area. Whoops, I did the wrong colors. There we go. So now if I add these two things up and factor out the 1/2 and the H, which is common to both of them. So again, I have a 1/2 here and an H. I have a 1/2 and H here. So by factoring that out, it's just going to be 1/2 times base 1 plus base 2. So there's our proof for our trapezoids area. Again, just splitting it into two triangles. Another way to do this is you can kind of imagine cutting this chunk and then pasting it over here. So just kind of like visually, if that helps you. Here we're going to look at an example of just finding this thing. So really the thing that I need is RS, which I'm told here is 5. And I need to know VT, which I'm told is 13. And I also need to know RW, and that thing is 6. Just be careful here because like ST, this is an example of a trapezoid which looks almost like a right trapezoid, and so we're not using ST, and we are not using RV for the height of this thing. It's got to be the altitude down. So now I'm just going to plug in my formula here. So let's say we used blue for base 1. We got green for base 2. And red for our height. So plug it in, do some math, and we get 54. So as we apply these things, hopefully it's pretty straightforward. Once you know the formula, you just plug in the pieces. Here we're going to talk about the area of any quadrilateral with perpendicular diagonals. So we have a couple things that have perpendicular diagonals. We'll zoom down here for a second. So the things that come to mind are a rhombus, a kite, and then also we want to remember that a square is also a rhombus, so a square would fit this description as well. So I'm just write in square here as well. So this again works for kite, squares, and rhombi. So as we look at this, it's going to be 1/2 diagonal 1 times diagonal 2. So those are the two diagonals in these figures. So with any quadrilateral that has perpendicular diagonals, we're going to get basically this diagonal times this diagonal to define the area of this thing. So if we think how how is this possible? I can look at this first one up here. I'm just going to say this diagonal's in red. So I'm going to talk about this in red here, and I'm going to make the top part a squiggle, and I'm going to leave the bottom part a straight line. So I'm going to kind of change my, whoops, oh, that was a poor choice. Let's just go back and do it this way. So I'm going to do the top as a squiggle, bottom as straight, top as a squiggle, bottom as straight. We will do green here for the left side as a squiggle, right side is straight, left side squiggle, right side straight. So again, red and green are two respective diagonals. If I wanted to talk about this triangle up here, AED, it's going to be 1/2, and then DE times AE. And I'm going to add that to this triangle over here, which is going to be 1/2 AE times EB. But really, instead of doing it as two little triangles, so again, if you want to look at it this way, you can. We can just do the larger triangle. So I personally would just do this larger triangle here, which I know the height here is going to be my red squiggle. And then I've got this length here, which is going to be my green squiggle and my green straight. So that's the area for this orange thing. I'm going to say it's 1/2 the red squiggle times, and I'm using super vague notation here because I want to leave it just so we can kind of visualize it without needing to dive into naming all these segments. So I get this big orange triangle on top to be this stuff. And now if I do the same thing, I'm going to do the same thing on the bottom. I'll do it in purple. So down here, I'm going to do a big triangle like this, and I'm going to do the same setup. So here now I'll try and orient it the same way. So as I'm orienting this triangle, here this is defined by the green squiggle, green straight, and now this is my red straight line here. So the area for this one is going to be 1/2. Oops. The red straight line, and then we have times squiggle plus straight line here. So as we look at these two things, this is going to complete this part over here. So if I wanted to just talk about this bottom purple triangle, this could be represented as, so I'm going to change the way I write it. So I'm going to say the area equals, and I'm just going to represent it in terms of the red times the squiggle green. So again, as this is intersected at a 90, we know that these two are equivalent. So I've come through and I've bisected this segment here. And so again, my right angle here giving me bisected. So green squiggle is equal to the green straight. So I'm going to change this. I'm going to call the area of this thing. Now I'm just going to say it is red straight times, and I'll say the green. So here I get a rectangle on the bottom. And now I'm going to add that to the same sort of equivalent thing on the top. So I'm going to change the way I represent my area here. And now I'm going to talk about this thing is going to be equal to let's get my colors here. Red squiggle. Oops. I accidentally included both these down here. Just meant to include one of them. It doesn't matter which one you choose, so I'm just using the squiggle one because it's more fun to draw squiggles. But again, we know those things are congruent, so green squiggle is equal to green straight. So as we're looking at this thing now, up top, what do I have? I have a rectangle represented by this orange, the orange triangle here, and then this other orange triangle added up, which is the red squiggle and the green squiggle. So here I've got area as red squiggle, green squiggle. I have area down here, which is red straight and green squiggle. So if I add these two things up, then the full area of this figure is just going to be the red, whatever the length is, and then times the green, whatever the green is. So as we look at this thing, when I'm doing the diagonal, it's just going to be half of the red times the green. So as I do this, I can represent it. I'll do it all the same. So I'll leave this as 1/2. I don't know if I'm going to be able to fit it, but I'm going to try. So red squiggle plus red straight, and here we got green squiggle plus the green straight. So again, as we look at these two things, we get one big rectangle here, which is going to be half of the product of those two diagonals. So hopefully this kind of makes sense for you. I'm just trying to represent it in a different way. If you just want to, again, think about these things, this intersects, creates two congruent segments here. So DE is the same as EB, and I have this segment down here, which is the same, except for I'm representing the height here as EC and the height here as EA. If I wanted to say this is a larger rectangle and just draw all of these out, each of these chunks are going to be 1/2 of that larger rectangle. So the easier way to look at this probably is just to look at this is the full red, and then this would be, you know, full green. If I just did red times green, I would get the area of the rectangle, and each of these chunks here, kind of think of them as 4 quadrant, is 1/2 of that quadrant. So 1/2 of all these quadrants added up is equal to 1/2 the area of the rectangle. So I kind of like thinking about it this way. If you just want to think about it as the way I just described, as each of these is 1/2 of those segments, and that's half of this full rectangle, then that's totally fine. So hopefully this didn't like throw you off too much. I know I made one little mistake here when I was writing the notation out for it. So again, if you wanted to think about it this way, great. If you want to think about it like I just described, that's fine as well. These are fairly easy to do. So we'll look at an example here of example 5. As I'm looking at this thing, we just want to find the area of this rhombus. I am told MP and I am told NQ. So basically I just multiply these two things. So as I'm looking at this thing, I didn't have the picture here, but let's do, whoops. So there's NQ. And we got MP. So here we got 1/2 of 12 times 16, and it gives us 96. So again, pretty straightforward and easy to do. Sometimes what will be given to you is like one of the side lengths, and then maybe one of these. So usually the one that will be given to you is the one that's being bisected. And so as I look at this thing, I know that I can use my Pythagorean theorem to solve for the length here and to solve for the length here. So that's kind of another twist on this type of problem that you may see. Last concept that we're going to get into here is a little bit hard to wrap our brains around at first. So I'm going to draw like a picture, and hopefully the picture helps before we get into the proof for it. If I draw this square as a 1x1 square, and I draw a larger green square as similar squares, so I'm going to split this and split this. And I know I didn't draw the red exactly the same because I didn't want the colors to overlap, but this I'm saying is a 1x1 square, and I'm saying this is a 2x2 square. If I want to talk about the area of this red square, I'd be saying it is 1 times 1, which is 1. If I want to talk about the area of the green square, I'd be talking about 2 times 2, 2 squared, which gives me 4. Now I want to relate these two areas together. So the relationship of the length for this was 1, and the length for green was 2. So if I want to talk about a ratio of the lengths, the ratio of the lengths would have been 1/2, or you could do 2/1 too. It depends what direction you want to go, but the ratio holds up either way, so it doesn't really matter. So here I'm going from red to green here, so 1:2. So now that's just for length. So that's talking about like sides. So now that I've got length, I want to talk about area. So we'll do area in blue here. So when I'm talking about area, area is going to be the length ratio, squared. So what I mean by that is my length ratio was 1/2, and now I'm going to square that thing. I don't know why I went back to orange for that. I guess maybe just to represent that, and then we'll square it in blue. So that gives me 1/4. Hey, look at the ratio we got here, 1:4. So as we do these things, say this is like 2:3, it would be 4/9 because I'm squaring that 2/3 ratio. So as I look at this proof here, just keep that in mind. When I'm doing this, if I wanted to scale this up one more and do another square, and I said it was like a 3×3, that 3 is going to get squared to be a 9. And we would see that represented in all these 5 cubes that we'd fill in here. 1, 2, 3, 4, 5. So looking at this proof, we're basically just trying to prove that relationship holds. So the area for one over the area of the second is going to be 1/2, or excuse me, not 1/2, the length of A1 divided by the length of A2 squared. So this A as a lowercase a is a side length, and that's represented right here. So what we're saying is this over this, so I'll represent it with a circle and a box. If I took that ratio and squared it, it's going to give me the area for this one, which again I'll put in a circle, to the area of this one, which I'll put in a box. So the way that we do this is we talk about, well, okay, I have to have a height on this triangle and I have to have a height on my other triangle. Now these two triangles are going to be similar triangles because I have some ratio between their two lengths. So for similar triangles here, we're not talking about like two totally different triangles, right? Those two triangles have to be similar to have this proportionality. So we're talking about all similar stuff here. So I'll just zoom back just for 1 second. So again, we got two similar triangles. This ratio holds. So as I look at this, I'm saying, okay, well, if I'm able to figure that out, I'm able to get the area for the first triangle, and the area for the first triangle is be 1/2 base times height. So I'm just calling this bottom B1 my base. So we're representing that here. And now if I want to talk about that for my larger triangle, I do the same thing, but now I'm using B2 to represent this base here. So using B2, here's B1. So as I look at these heights, I'm saying, okay, well, the height of this and the height of that are proportional. Keep that in mind. The height of the base of the first one and the base of the second one are going to be proportional. Keep that in mind. 1/2 over 1/2 is just going to cancel off. So basically, these 1/2s disappear. So this is gone, and I'm left with B1 over B2 times H1 over H2. Now, keep in mind that when we are doing this, this ratio was the same. So whatever B1 over B2 was, and whatever H1 over H2 was, they're the same. So instead of representing this as B1 over B2, and this is H1 over H2, I can switch this, and I can talk about their side lengths. So here's where we're saying, okay, let's talk about their side lengths. I've used enough orange. Let's switch to blue here. Let's talk about their side lengths, right? So my base is going to be proportional, and I'm going to have the same property with my height. So as I look at my height, it's going to be proportional as well. So if I've got these two things which are proportional and they're the same, then I can just say, okay, let's have a substitution where instead of writing A1 over A2 or B1 over B2, it doesn't matter what variable you're representing with, let's just use the same one twice. So let's use A1 over A2 twice here. If you want to do B1 over B2 and B1 over B2 again, that's totally fine as well. The substitution comes out to be the same. So we plug this thing in, and here now we have our representation of this value squared, and that's going to be the ratio of my areas. So again, as we're looking at this, hopefully it's not too difficult. If I gave you a triangle and we had an example here we can look at, we're able to figure these things out. So let's look at this thing. So here we're talking about two similar triangles. The first triangle sides are half as long as the triangle, the second triangle, excuse me. So when I look at this, S1 equals 1/2 of S2. So basically, here is my ratio. My ratio is, it's 1/2, right? This is S1 stuff to S2 stuff. And 1/2 is representing the ratio. If I gave you an actual length of this thing, like if I said the top one was 5, we would know the bottom one would be 10. So here's S1 over S2. It equals 1/2. Now, as I look at this thing, I'm saying, okay, well, what if I want to talk about the area of this thing? Okay, well, if I want to compare their areas, then I'm going to take this ratio and I'm going to square it. Equals 1/4. Perfect. And we can see that in the picture here. So this, which used to be one little triangle like that, is now one little triangle, two little triangles, three little triangles, four little triangles. So again, we see that by doubling the length here, we actually quadrupled the area. So again, when I take the ratio of the lengths, I square that, and that's the ratio of the areas. So in the next example here, we're looking at two squares. So the first square is 3 times as long as each on the second. So here we're representing these two squares. I would say my ratio is 3:1. So again, if you wanted to call this 1/3, it wouldn't really matter. It just means you're talking about them in reverse order. So it's more just an orientation of what you call your first and second square than it is anything else. So as we look at this thing, it's 3:1, and this is for the sides. So if I want to go to area, I want to be talking about 3/1 squared. So we've represented 3/1. Just keep in mind that we do have our ratio that we're comparing and everything. But if you just wanted to have it written as 3, that's totally fine. And that equals 9/1. So again, here, just doing that to keep in mind we're talking about the ratio. So as we look at this thing, if I told you the area of the first one is 9, we know the area of the second one is 1. So 9 times as great as the first. And the sides are only 3 times as long. So again, we're taking that side ratio and we are squaring it. And that's all we got for 8.2.